So it turns out that how fast you burn through your fuel as a star depends really sensitively on the mass of the star. So a very high mass star has lots more fuel to work with, but it gets through it really, really, really fast.
Yeah.
So low mass stars, there are stars still shining today that were formed in the first billion years of the universe or less. Some of those are still going, and they can keep going for a very, very long time.
I can't think of any more human activity than conducting science experiments.
The game I play is a very interesting one. It's imagination in a tight straitjacket.
The beauty of a living thing is not the atoms that go into it, but the way those atoms are put together.
What I always think should be the basis of education is not answers, but questions. We should teach kids how to question.
Well, I'm Nick Tothill, and I'm an astronomer in the School of Computing Engineering and Maths, and I'm currently the director of the Western Sydney University Penrith Observatory.
Ah, awesome. We've been out to the observatory, and it's great out there.
We had Aim the Hoarder on, as well as Elena Hyde from the observatory, so really interesting people to talk to.
Yeah.
So there's been some interesting developments recently.
Yeah, we got you on because obviously you probably have an opinion on the recent finding of water on Mars, and actually I think you were asked to comment on the Gizmodo article that was recently written about it as well.
Yeah, well, I should probably mention I'm not a Martian geologist, or even still less a Martian glaciologist, which I guess is now a new speciality. But yeah, when I saw that discovery coming in, it was really pretty amazing.
Yeah.
Because we have liquid water under the Earth's ice caps in Antarctica, and it turns out we have it on Mars as well. In fact, when I read it, it was like, oh, of course there could be.
Yeah.
I'd never thought of it like that.
Yeah, same. Like I'd heard that they'd have like frozen water on Mars and the ice caps, known that for a long time and things, but never even thought about it underneath. And because there's other places like you were mentioning today to me, Hamid, about Europa and things like this as well, which have oceans under ice in other parts of the solar system.
Yeah, we're pretty sure that Europa is essentially a whole ocean. The ocean covers pretty much the whole moon under the ice, and there may be something like that on Enceladus as well, around Saturn's moons. We know there are lakes on Titan, but they're made of hydrocarbons, so it'd be like a lake of diesel or LPG, I guess.
Yeah.
And kind of like the size of the Great Lakes.
No oil companies are
I was just saying,
planning trips yet.
we invest all the money, take it out of renewable resources and send it to like the moon.
Yeah.
Oh, that's interesting.
What are some of the details? You may know more than me, but of the recent finding of water on Mars, I read somewhere that the water's, they think, about 1 meter deep, and it's mostly kind of like sludgy.
Well, we don't really know terribly much about it. We can see the horizontal extent of it. We can see that the lake's about 20 kilometers across, which is a good size.
Yeah.
We know that the depth has to be at least a few tens of centimeters. Otherwise, you wouldn't get the radar echo. So this is actually, this was found by doing radar studies. So you actually do radar observations of the surface, which is how you find the lakes under the South Pole, under the Antarctic ice cap. So it's the same technique. And you need at least about a few tens of centimeters of water to be able to generate the echo. That's what you actually see.
Is that because of the the length of the wave, or why?
Yeah. It's a pretty long wave, so you just need a long enough water thing to actually reflect it back.
Why do you think this wasn't discovered earlier? Is it people just didn't look, or was there technological limitations?
This is already right at the limit of the technology that they've got. I mean, so this was first suggested apparently about 30 years ago. Somebody was suggesting, hey, we think we've got water ice caps on Mars. You could have lakes underneath. And they ran some numbers, and it seemed plausible, but nobody had actually found it. And actually finding this lake was right at the limit of what you can do with the radar instrument that's on the satellite. It's basically about as small as you can see with that radar, and there are a lot of limitations compared to how you would do it on Earth. So it was a hard thing to do. So it's taken a while.
Yeah. Sorry, you're going.
I was going. Yeah. So how many obviously my next question was, okay, this radar has to be on something. You said it was on satellites, and they have satellites orbiting Mars. When did they install this radar? I'm just curious. Was it something new that they just sent off recently?
It's the Mars Express mission has been around for a while, so it's not a very new thing. It's really people using a satellite that's been there for a little while to do something new.
Okay. Let's move on to the implications of the finding.
Yeah. Why are we so excited about this discovery, right?
Well, because in the immediate term, what it tells us about is about water on Mars, about the history of water on Mars. We know that there was liquid water on Mars because we can see old dry lake beds, we can see old rivers. You look at this landscape on Mars, and it was created by water a long, long time ago. So we know there has been liquid water on Mars, and there isn't anymore. But we know that it's locked up in the ice caps. So when you think about, one of the things that you want to understand is where the water on Mars went and how it operates now. Does it all just sit there on the poles, or does it move around a little bit? Is there actually a little bit of water activity? And of course, the elephant in the room is, what can this possibly tell us about whether there could have been life on Mars previously? Because if there was a whole load of liquid water on Mars, could there have been life? And that's a big question. And you could even, if you really wanted to speculate, you can even say, well, if there was life on Mars, could it be surviving? That would be pretty impressive.
Yeah.
But now we know that if we're interested in understanding liquid water on Mars and trying to understand what that meant for life, now we know where to look. And we can even, and of course the other thing is that they basically didn't have a lot of data, and they found a lake.
Yeah.
What we haven't done is map the whole of Mars this way. So there could be a lot more. In fact, the fact that they looked at a little bit of Mars and found a lake, kind of at a very basic level, suggests that there probably are quite a lot more.
If you got lucky that early with such limitations on the equipment.
Then either you got really lucky, or there's a lot of liquid water sitting under these ice caps. And it could even be connected. We think that the subglacial lakes in Antarctica, some of them have channels between them, which are these kind of subglacial rivers. So could you have those on Mars? You could actually have a whole hidden hydrosphere of water moving around underneath the ice.
And like you say, like rover expeditions are incredibly expensive and take a long time to set up. But now that we know we have a place where we can go and look and find liquid water, that's a very tantalizing kind of destination.
They send those rovers to find indications of life, right? And getting them actually on Mars without being destroyed is a huge challenge.
And also, and if you think it's easy, just look at the numbers that didn't work. So it's easy to get blasé and go, oh yeah, you just landed on Mars, and then one of them crashes, and you go, oh you mean that's hard?
And I think recently they have almost like a drone thing that they're trying to send off to Mars. Thunderfoot was covering that. And even that, like, it can only be up in the air for like a minute or 30 seconds. It can't really survey the surface of the Mars. But this technology seems to be a great way of probing the presence of water on Mars. Now, some people might be listening to this and say, how could life even survive on Mars to this day? Like, that's crazy. Like, Mars is basically the most arid desert you can think of. Even if there is water, it doesn't have oxygen.
Little atmosphere to protect it from
little atmosphere. But people may not be aware of the extremophiles that exist on Earth. We have what's that thing called, the tardigrade? Or what? Have you heard
the
of it?
tardigrades.
Yeah.
But also the species of bugs that survive in some very, very unpromising places. And you've got the halophiles, which live in incredibly salty brines. You've got thermophiles who live in very hot conditions. You've got the ones who can live in incredibly cold conditions.
Then they also find some around Fukushima that can live in with high radioactivity as well.
I haven't seen the Fukushima ones, but I remember there are bugs living in the flooded 3 Mile Island reactors that were flooded when I was a kid. So Mars is not a hospitable environment for life, particularly complex life. There are things on Earth that survive in extremely harsh environments. So what you could maybe be looking at is that you could have had primitive life on Mars, which has managed to cling on through these incredibly tough environments.
I guess one implication we haven't really discussed as well is about the possibility of future travel. A lot of people are, they've got all these Mars expeditions being planned. What is the finding of this water? Does it have any implications for travel? Or
I was just going to ask, before we change topics, keep that question in mind, Nick. I think one more thing that the implication of this if we do find life on Mars, is the idea of panspermia. Where did life come from?
Right.
Because if asteroids hit planets, like I don't know if this is correct, but I've heard from people that if an asteroid hits the Earth, the debris can also reach the Moon if it's big enough. So it's possible that an asteroid has hit Mars, and then bits of that debris has made it through space and actually hit Earth, and then that's seeded life here on Mars, on Earth.
Well, we know that some pieces of Mars do end up on Earth. So there are meteorites that were found in Antarctica, where you actually do the analysis and you realize this isn't your normal little piece of solar system debris. This is actually a little piece of Mars rock, and so that's actually happened. Something hit Mars, threw up a debris plume, and these things just floated around the solar system for however many millions or billions of years until they eventually fell down on an ice sheet in Antarctica. So that does happen. And so then, but then of course it could go, on the one hand it could go either way. If that actually does work, then, did Earth contaminate Mars, or did Mars contaminate Earth?
I was just about to say that. It's a very difficult question. Like, imagine that you go to Mars and you find traces of life, and you can test that life and say, it has DNA like on Earth. How do you make that inference then that that's because life was seeded from Mars, or could it be a contamination that we're brought to Mars, or could it be
through
from Earth?
asteroids?
Yeah, exactly.
That would be tricky, wouldn't it? But it would be cool if we find a new type of life that doesn't have DNA or RNA. That'd be fascinating.
It would have a completely different way of information transfer.
That'd be interesting.
Be a hard thing to do.
So maybe let's jump back into that travel question now. Because a lot of people are discussing going to Mars in the future and setting up colonies. Obviously, the fact that we find liquid water on Mars is kind of promising for that type of thing, or am I missing the mark there?
Well, if I was on Mars and I wanted
Sorry, we're not getting level.
A few moments later.
Do you want to do the question again, or shall I?
Let me do it again.
Get straight in. Okay.
Take 3 on the water on Mars question. I said it good the first times as well. Okay, so we're thinking lots of people are planning trips to go to Mars, right? And live on Mars and form colonies on Mars. And obviously water is a major concern there. Are there any implications for this finding in terms of colonization of Mars and future travel?
Well, if I was on Mars and I wanted to get liquid water, I would sit on top of the polar ice cap and I would melt the ice. Because that's what we do in Antarctica. In Antarctica, you just melt some snow. And there are some pretty sophisticated ways of doing that. Drilling it out of one of these subglacial lakes strikes me as not the best way to do it, because first of all, you've got to drill a kilometre or more down. And secondly, we're pretty sure that the water is incredibly briny, because that's how it would stay liquid. And it's not just sodium chloride, it's perchlorates of several different elements, which I think you guys are better chemists than I am, but I'm guessing not very drinkable. Yeah. And also there's as the discoverers have said, it's this may not be, if you're imagining some beautiful gin clear pond, it may not be that. It might actually be what they actually call sludge in the science paper. And I think
not exactly a scientific term, but
I think it's a great victory for scientific accessibility, because I was reading the editorial accompanying it, and it talked about saturated sediments, and I was thinking, well, what saturated sediments? What is that? And then I read the actual science paper, and it said it could be sludge. I thought, sludge. Okay, I know what that means. So basically, it's until you actually understand more about it, it could be a lake of beautiful clear water, or it could be a layer of thick briny sludge.
That's funny. It's funny that scientists, in their pursuit to be clear and as precise as they can be, make it really convoluted in the process.
Yeah, well, when I read saturated sediments, I thought, is it more like kind of wet sand or clay?
Yeah.
And it's like sludge.
Okay, it puts a picture in your head.
Got it. Yes, yes.
Maybe we can move on to your journey a little bit now and talk about, because that's where we usually start with our guests, because this shows it shows about trying to tell people what it's like being a researcher and being a scientist. So what got you into like astrophysics or astronomy, or into science in general? You can start as early as you want as well, like you don't have to start with your PhD.
Well, I didn't, because when I was a kid, I got a book about astronomy, and I thought that was just the best thing ever. And at some point, I found out that there were people who actually did this. That when you grew up and you had to get a job, there were some people who did astronomy for a job. I was like, okay, that's what I'll do.
Yeah.
And then from there on, that was what I wanted to do. So I went off and I did physics at university. Then I went and did research for a year in Germany, and found out, doing astronomy, and found out, this really is fun, because you always wonder, it's like, is this as much fun as it sounds?
Stuff can look fun on the outside, and then when you actually get into it, like, this is terrible.
And actually, I found I really enjoyed doing it.
Yeah.
And so then I did my master's degree at Jodrell Bank, doing radio astronomy, and then did my PhD in submillimeter wave astronomy, looking at the very high frequency radio emission from gas clouds in the Milky Way, where stars are forming. And that was in London. And then from there I bounced around a little bit. I went to Canada, and then the US, with side trips to Antarctica, back to the UK, and then I came out to Australia.
Tell us about your trips to Antarctica. What was that like?
That was a lot of fun, because it turns out that Antarctica is a great place to put telescopes. And
why is that?
Because depends a bit on the telescope, but mainly because it's dry. It's very cold and very dry, because all of the water vapor in the atmosphere has already frozen out and is sitting under your feet.
So does that mean it's dry, it's less humid, so there's less, obviously we just said water in the atmosphere makes cleaner viewing?
Yeah. So for some quite specific types of astronomy, the water vapor in the atmosphere actually absorbs the light that we're trying to look at. And so if we can go somewhere very dry, like a desert, or an ice cap, then it's a great place to put a telescope.
I have a practical question. So a lot of people might not realize, but when you have telescopes, you have to acclimatize them to their environment. So if a telescope's really warm and it's kind of like cold outside, that can warp the lens and affect the viewing. What's it like acclimatizing a scope in Antarctica, or how do you deal with that problem? Or do you just have to put up with the cold, or do you keep the telescope warm, or what do you do?
You generally try to keep everything, trying to let the telescope go to its environmental temperature. Once you've got it there, actually everything kind of helps you out a little bit, because you don't get extreme diurnal cycles in Antarctica. At the South Pole, day and night don't count. So you're not going to get it suddenly getting cold at sundown. Well, you do, but sundown happens once a year. So it's so in that sense it's quite good for the temperature stuff. On the other hand, when you're designing it for the first time, you have to think quite hard about how it's going to work in about minus 50 degrees. And luckily I didn't do that design work. My boss did, and he did a very nice job.
No, that's awesome.
So when you're using the telescope, maybe not obviously, but the observatory itself would be kept cold, because you don't want to have a warm environment.
Well, the telescope sits on top of a building, and so it just sits out there. So I have a warm building, and I can sit in the warm building and do stuff, and then the telescope sits on the outside. And I just got cold when I had to go and mess with stuff on the telescope, which was a little more often than I might have liked. But,
how long were you in Antarctica for?
Well, I was there for a year, where I basically did the summer to learn how to use the telescope, and then did the winter time, which is a 9-month stint. And the winter time is when you actually do the work, and the summertime is maintenance and just making sure, changing out spares and stuff.
Give us some of your highlights, some things that stick out in your mind from that experience.
I'd like to hear highlights and lowlights. Like what were the things that were amazing that you were one of the select few people in the world to have seen, and what are some of the things that were terrible that you're probably one of the few select people in the world to have experienced?
Well, one of the highlights was actually the just looking up at the sky, seeing the aurora. The southern lights are moving around, and just deciding I don't need to go anywhere for a while, and just lay down on my back on the snow, just watching these green kind of knots and ropes moving across the sky. That's cool. And then you kind of look up and remember that they're at about 100 kilometers altitude. Those are really big, and they're moving really fast. That was, and just looking out over the ice cap. It's completely flat. It's just this completely flat snow surface. There's no dirt. There's just nothing but white and a sky, and seeing that in the dark under a full moon is that was pretty awesome.
Yeah, that's cool.
And the lowlights were stuff like well, at one point it was just the basic as once I got my I left a little gap between my scarf and my goggles on the walk back because the telescope's about 1 kilometer's walk from the station. Jeez. And I was walking about 1 kilometer into a bit of a wind, and I thought, oh man, I left a gap. Oh, it'll be all right. And walked there, and I ended up with like a very low-grade frostbite just across the bridge of my nose, and I couldn't wear my glasses for about 3 days.
Oh, jeez.
So that was a low light. So sometimes you just do get really cold.
I guess those things would impact you in lots of tiny little ways that you don't even think about, just like time to get dressed and time to get ready and prepare, and everything would be and if we ever had a power cut, because we were running generators 24/7, but if we ever had a power cut, then I had about 20 minutes to get out to the telescope, power everything down safely, and phone it in, which was quite tight, especially if it happened in the middle of the night. And I once asked the station manager, look, what actually would happen
do we really have to get the generator back up that fast? And he said, after 40 minutes, I start deciding whether or not we go to our contingency plans for, basically living in tents for the rest of the year. It's like, oh, okay then.
Yeah. Wow.
Is that because the generators would freeze or things won't be?
Basically, it's what you would have to do is you have to warm up the summer camp, which are these insulated tents. They're not as bad as it sounds, but you would have to start warming it up, and it's way easier to start warming that up while things are still warm, rather than when everything's gone cold. The contingency plans. I didn't know a lot about the contingency plans, but I think they were pretty scary.
Well, it's good that you didn't know about it because you didn't have to use it.
I also imagine, getting back to what you said about the highlights, because I've been lucky enough to see some night skies away from cities in the outback and things like this, and they're next level. Like, it's the type of thing where you look up and you go, oh my God, what is that? And then you realize it's like the Milky Way, and that's what the night sky looks like when you get away from all the bright lights of a city. And I can imagine that would have been next level again in somewhere like Antarctica, where you don't have the atmospheric disruption or no lights at all.
You'd have these really great, just kind of very clear nights with nothing moving around, and then if you had a full moon, then it was like being outside in the middle of the day. You could see absolutely everything. And if you had no moon, it was pretty dark.
That's cool.
And the Southern Lights must have been almost psychedelic.
They were, and we had a good year for them. Because it depends on how the sun's going that year.
Right.
If there's a high solar activity, then you have a lot, and if it's low solar activity, you can hardly see anything, which would be a bit. I'd be a bit disappointed.
It would be,
It's like my year at the South Pole. I can't see the aurora.
lights. You just see it on one day. Speaking about the sun, I think that's a good.
Well, you mentioned before as well. That when you were going through your journey, that you'd done some research on stars and star formation
from galaxy gas clouds. Can you tell us a little bit about that?
Because stars have a life cycle, don't they? So maybe run us through the life cycle of a star.
So stars start out as big clouds of gas. So in a galaxy, you have a bunch of stars, which are the things you can easily see, and you have big clouds of gas and dust, and you can see those as the dark spots. So if you go out somewhere nice and dark and you look at the Milky Way, the first thing you see is there's this incredible bright band across the sky. The next thing you see is there seem to be holes in it, and they're not holes in the Milky Way; they're just dark clouds. And that's actually the shape that indigenous people had as an emu in the sky. It was actually made up of those dark clouds. And so those dark clouds are where stars come from. So a star formation is a simple process that you start off with a cloud of gas and nothing else is happening. Well, gravity is still working. All the atoms in it want to kind of attract each other. So the whole gas cloud kind of falls into itself and becomes, from a very big, very tenuous, very cold gas cloud, it turns into a very small, very hot, very dense gas cloud, which is basically a star. So at this really basic level, star formation is an incredibly easy process to explain. And then actually the question is, well, why doesn't it work quite that way? And that's where you get into some issues around angular momentum, transport, and magnetic fields and fun stuff like that.
Let's just quickly go back. So if the dust is condensing under gravity, why doesn't it just keep condensing? What stops it kind of condensing indefinitely?
Because it turns into a star.
So there's I guess there's like a fight then. So when it condenses enough, it turns into a star. Work us through that. What turns on? What happens at that point? So
when something gets dense enough, as things get denser, they get hotter. And once something gets dense enough, then all of the atoms are hitting each other, and eventually the atoms are hitting each other hard enough that the hydrogen atoms fuse together, they stick together and become helium atoms, which is exactly what happens in a hydrogen bomb. So at that point, you start releasing a lot of heat and a lot of energy, and everything starts moving fast. And what happens is that energy release pushes back against the gravity. And at some point, you reach the stage where the two are in equilibrium. So one way of thinking about it is that the gravitational collapse is halted by the energy release from nuclear fusion.
Yeah.
Another way of thinking about it is that it's actually a gigantic hydrogen bomb, and if you imagine a hydrogen bomb where the fireball is expanding out until it gets to the point where it wants to fall back, and you just hold it in that balance.
So it's like these two forces are kind
Yeah.
of like fighting each other and just
Yeah.
holding this stable
that's a
structure
star.
that we call a star.
Yeah. And that equilibrium lasts for millions of years for big stars and billions of years for small stars.
So
And that's because bigger stars burn hotter, and so the energy to actually maintain the energy coming out of the star, the center of the star, is burns quicker, and so that's no longer available, and so it collapses on itself.
Yeah.
So what you're saying is the life of a star then it gets birthed when this matter condenses enough to get the energy going, and it lives while we're maintaining this equilibrium. And as Hamid just said, once that fuel of the fire, all that matter burns out, I guess the equilibrium can't be maintained anymore.
Yeah.
Yeah.
So you run out of fuel. So that's the point where you figure, okay, it's all over, except that actually a whole load of stuff happens in the late stages where suddenly you start fusion reactions with helium and then all kinds of other stuff, and you get explosions. And so different stars, based mainly on how heavy they are, will have very different end stages of their life. Some of them just kind of go dark and that's it. Some of them turn into white dwarfs, some of them turn into neutron stars, some of them turn into black holes. You get supernova explosions, novas, all sorts of...
This sounds just like human beings. You know, some people die at an elderly age, and they've had a nice, easy life. And then you have rock stars that are coked up and party hard, and they go out with a bang.
The high mass stars, live fast, die young, and leave a good-looking corpse.
So you mentioned that stars, the birth of a star doesn't always happen, that there are different variables that actually are involved in initiating that process. And you mentioned a couple. Could you just...
Yeah, I thought maybe we could work through them a little bit more detail. So maybe let's start with not with the rock stars, because then we can end the conversation with a bang. So how about we start with like these low mass stars, right? So we've got stars that have low mass in them, so they're not going to burn as hot. So it's kind of counterintuitive, I guess. You think low mass, low matter, they're probably going to have a short life, but they don't actually burn as hot, so they have the longest life, don't they? Yeah.
So it turns out that how fast you burn through your fuel as a star depends really sensitively on the mass of the star. So a very high mass star has lots more fuel to work with, but it gets through it really, really, really fast. So low mass stars, there are stars still shining today that were formed in the first billion years of the universe or less. Some of those are still going, and they can keep going for a very, very long time, which is good because that's one of the ones that's the kind of thing we live around. The sun isn't the lowest mass kind of star, but it's kind of moderate mass. It's got billions of years to work with, which is good because we needed billions of years to get here, it seems. So that's worked out pretty well for us, and we've still got a few billion years of the sun doing its thing. And the sun is also very stable. It does change, but it doesn't change fast. It doesn't seem to change a lot. So that's good for us.
So what happens then for these small to medium mass stars? What happens when one of these stars dies?
Well, what happens is that as it gets older, it eventually becomes a red giant. And what's really happening is just that equilibrium is being disturbed, and it's finding a new phase, a kind of a new equilibrium where it's still producing energy, but it gets much bigger. But because it's much bigger, it's actually much cooler because it's not producing enough energy to stay to keep something that big that hot. So that's when we become a red giant, and when the sun becomes a red giant, then the sun, well, the Earth will end up inside the sun, but
So
not
it
for very
expands
long.
that much then?
It expands past the orbit of the Earth.
Wow.
So that happens, and then that lasts for a little while. It doesn't last terribly long.
Yeah.
And along the way, after it's been a red giant for a while, it moves into a phase where it actually starts pumping a lot of its mass out of the star. This turns out to be a really interesting phase for the galaxy, because then a lot of the stellar mass is returned to the gas in the galaxy. And it's not just returned as the way it was before. It's been enriched with elements like carbon, nitrogen.
Yeah, well,
and
I was just
oxygen.
about to ask that. Yeah, so it's emitting like its constituents out into the galaxy. So what is that? You just said the carbon and
Yeah. So the gas that creates the star is almost entirely hydrogen and helium, with a few little bits and pieces. But the stuff that comes out of the star at the end of its life has a lot more of the more interesting elements in it, like carbon, nitrogen, oxygen. We don't get the really heavy stuff. That has to come from supernovae.
So
But
up to a certain point on the periodic table. Yeah.
Then, so most of the carbon, and if you think about all the stuff that's doing most of the work in your body,
Yeah.
most of it is those comparatively light elements. It's not the iron and stuff that
Yeah.
you need it. It's mainly carbon and oxygen, stuff like that. And most of that actually comes from these low mass stars.
That's cool.
Just pushing it out at the end of their life, and then that can get turned into new stars.
Just a question. So, in the universe, are there more low mass stars than there are like these larger stars? Because I'm just thinking, if life comes from these low mass elements from the periodic table, it must mean that there's more of that available in the universe, maybe, and that's provided opportunity for life to evolve with these elements. Whereas if it was more higher mass elements, maybe those are more rare, and therefore there wasn't an opportunity for life to evolve with those.
Yeah, so you have far more low mass stars than high mass stars. It's much easier to make them, and of course they last longer. So that also gives you a kind of a lifetime effect. And that does mean that the composition of the universe is much more biased towards light stuff than heavy stuff. It's much harder to make the really heavy elements. But as the universe keeps evolving, more and more heavier and heavier elements get made, because the universe has quite efficient ways to turn light elements into heavy elements, but there aren't really many ways to turn heavy elements into light elements.
I wanted to zoom in on that a little bit, because I think we kind of glossed over it a bit, because it's actually really amazing, isn't it? A lot of people who are listening to this may not even realize that they may not have even thought, where do the atoms come from the periodic table, but they're actually formed, right? Like if you wind the universe back to when stars were just being formed, there was just hydrogen, right?
Well, if you wind the universe back to the Big Bang, then the Big Bang creates hydrogen, helium, and tiny, tiny amounts of lithium and an even tinier amount of beryllium.
So these are the first 4 elements on the periodic table, right?
They're very light ones.
Yeah, 1 proton, 2 protons, 3 protons, 4 protons.
Yeah.
Yeah.
And if you think about what you can do with hydrogen, helium, lithium, and beryllium,
Yeah.
it's not a whole lot.
But you can form stars.
But you can make stars, and it turns out that stars are basically these tools to make the universe more interesting.
Molecular factories. Yeah.
Well, they're atomic factories.
Yeah.
Well, some of the cooler stars have molecules in their atmospheres as well. Things like titanium dioxide. Actually, you find it within the cooler red stars, the red dwarfs.
Yeah, that's really interesting.
That's so we talked about how these stars are born. Now, stars also initiate the life, or the explosion of one star initiates the life of or the birth of another star. Could you? Is that the case?
We think so. That's actually still a matter with a little bit of it's still some debate as to exactly how that works. But it does appear that the way to once you have one of these gas clouds sitting in space, one of the best way to actually get it to form stars is to compress it, to give it a bit of a push, and one of the ways of doing that is the shockwave from a supernova.
That's a nice segue, because we talked about the low mass stars and how they die. Maybe we can talk about supernova now, because it's basically the death of a high mass star, isn't it?
Yeah.
Yeah.
So a high mass star will what it will do is it will start burning. It won't just fuse hydrogen into helium. It'll fuse helium into other elements. It'll form carbon, nitrogen, oxygen, silicon, and so on. It gets all the way up.
Is that because it's got enough energy to push those protons together?
Yeah, it's basically the mass. It's
Yeah.
just so heavy that the pressures at the center can be high enough to actually push a bunch of helium atoms together, not just hydrogen.
Yeah.
And so you're able to carry out extra nuclear reactions. And those extra nuclear reactions actually keep it going past the point. Once it's run out of the hydrogen that it can burn, it can now burn other things. And so that keeps it going, but for less and less time. So it's kind of keeps going in a new, and every time this happens, it kind of, you get a flash and it changes a little bit. And eventually it gets to the point where in the middle of it, it's iron. And it turns out that as you keep fusing elements together and making them heavier, you get energy out. But iron is the most stable nucleus.
Yeah.
And so if you want to make anything heavier than iron, you're not getting energy out anymore. You're sucking energy in.
Okay.
At which point the star suddenly goes from releasing energy to pulling energy in. And the whole equilibrium is completely thrown out very, very quickly.
What's very, very
whole
quickly
star
in
explodes.
stellar terms?
Well, a supernova, in terms of the time it takes between running out of fuel and the supernova happening, I'm not sure.
Yeah.
But the supernova itself happens in kind of less than an hour.
Wow.
And then
I thought you were
the
going to say
expansion-
weeks, and I was getting ready to say, wow, that's so
yeah.
short. But an
I
hour.
mean, the
yeah.
expansion will
Amazing.
take as long as it takes.
Yeah.
But that initial explosion is incredibly fast.
Yeah.
Because it's basically the whole star.
Yeah.
So it's...
Does that explosion leave anything behind, or does it just vaporize and it send everything out?
So it pushes a lot of stuff out,
Yeah.
and that's why you have these objects called supernova remnants, which are these gigantic bubbles of gas that are the stuff that's ejected out. But you still have the core of the star left in there. So what's actually happens is essentially you've got an iron core, and the star has collapsed onto it and bounced. And that's kind of how the supernova works. But when it's actually bounced off the core, it's compressed the core as well. And the core gets compressed into either a neutron star or a black hole.
What's a neutron star?
Well, a neutron star is made of a material where everything has been compressed so much that atoms basically don't exist anymore. So an atom is a nucleus with a bunch of electrons around it, and the electrons, when you push on an atom, the electrons push back, and so the atom seems to have a kind of size.
Yeah.
Well, if you actually squish the electrons hard enough, then they get squished into the nucleus, and they combine with the protons to form neutrons, and instead of having atoms which are basically empty space, you just have a whole load of atomic nuclei, basically all neutrons. You kind of get a fluid of pure neutrons.
Yeah, it's interesting
faintly crazy.
because an atom is, a lot of people don't understand. A lot of people understand that an atom is a proton and neutrons in a nucleus, and the electrons are around the outside. But a lot of people don't understand that distance between the nucleus and the electron is huge. I know, I've heard lots of analogies, like a tennis ball in the middle of a huge stadium is like the tennis ball is the nucleus of the atom, and the electrons floating around the seats of the stadium. Like that's the distance we're talking about here. And you're saying is a neutron star is when we're pushing that seats around right up close to that tennis ball in the middle of the stadium.
Yeah.
So it's incredibly dense.
Or it will be like going from the tennis ball in the middle of the stadium to a stadium full of tennis balls.
Yeah. because when we push the electrons so close to the nucleus of the atom, that lets us put more atoms closer together. Yeah.
So basically you end up with just a whole load of nuclei all packed in together, which is
Yeah.
why neutron stars are incredibly dense.
1 second. I've heard an amazing fact as well, and I don't know if this is bunk. I can't remember where I heard it, but let me ask you. If you took, like, say, a ball of neutron star and dropped it through the Earth, it would go all the way through because it's so dense. Is that crap, or is that like...
It would leave a pretty big hole. So yeah, I mean, I guess what it would just do is it would just kind of drill a hole through and then kind of bounce back the other side.
Yeah.
Or something. But yeah.
Yeah.
So
Interesting
that's probably
thought
what a black
experiment.
hole is. Yeah.
Yeah.
Please don't do it when I'm around.
Yeah.
So how are black holes different from black holes are also really dense, and they form as a result of supernovas. But when the supernova, when that star takes that trajectory, how is it any different to a neutron star?
Well, a neutron star, there's still actually there's real matter there. There's neutrons, and you can do physics about the physics of neutron stars, and there are all these really strange quantum effects in there, and neutron stars have starquakes and stuff like that. Mm-hmm. A black hole is where the mass is packed so tightly that there's no real structure to it. There aren't even neutrons or electrons. It's just matter that's packed so tightly that even light can't escape. And we call it a singularity, which is a pretty clever way of saying that we don't really know what it is. But at that point, you don't even have neutrons. You don't even have that particle structure of matter anymore. There's just mass in an incredibly tiny space. So black holes are. A black hole really, in some ways, hardly even exists. The event horizon of the black hole is what exists, which is just the point where, there's once you're past that event horizon, once you're inside it, then that's you're not getting out, which is why black holes always seem really creepy.
I had one quick question about so we've just been talking about supernova. Yeah, we've been going on for a long time already. So much interesting stuff to discuss. We talked about supernova. How rare are these events? Because we mentioned before about the low mass stars are very common, but how frequent are supernova? Are they happening all the time, or?
They're happening, well, in our galaxy, we expect about one supernova a year.
Okay, yeah.
So most of them obviously happen on the far side of the galaxy and are hard to see.
Yeah.
But we expect something like that. They do happen kind of all the time.
Yeah.
But the last time we saw a supernova that was really easy to see in our galaxy was hundreds of years ago. Because they need to be close by for us to see them. For us to be able to really see what's going on.
I was before you shifted the topic, and maybe we can kind of like wrap it up soon, because I know you probably have things to do, Nick, and we've been going on for almost 50 minutes now.
Okay.
Time flies with these sort of conversations. That when you describe the black hole, where matter basically almost like becomes one thing, where there aren't any distinguishing factors like nuclei or whatever. It reminded me of a book that I was reading by Lawrence Krauss, The Greatest Story Ever Told, and he was talking about superconductors.
Yeah.
And it reminded me of how like superconductors function almost as one entity, and it's very analogous. What are your thoughts?
Yeah, well, superconductors are one of these strange things where these incredibly microscopic quantum effects suddenly appear in the real world, because you've actually got these pairs of electrons which are able to function as frictionless particles. So in some ways I think I would probably draw more of an analogy with neutron stars, where again you have the actual the quantum effects with all of their strangeness actually show up in real measurable things. And so that's a really strange thing when you see a superconductor. It's just you get something, and it's not and you just make it cold enough, and suddenly,
Yeah.
a magnet floats or something like that, and that's just that's quantum physics suddenly showing up at the
Macro
level of
level.
your hands,
Yeah.
which is really strange.
Yeah.
Quantum physics is a lot easier to deal with when it doesn't intrude on your everyday,
Everyday intuitions, eh?
even though it does all the time.
Yeah.
You just don't notice it.
Yeah.
That's funny. Okay, so we're reaching about 50 minutes now. I guess what I want to end with is just to get you, to ask you if you're doing any sort of research projects, taking on research students, PhD or MRes students at the moment.
I work with a few other astronomers in the school, and we always have research students around, and we're always looking for people who are interested and want to do this kind of stuff. So we're working on getting the mapping out the local universe by looking at the redshifts of local galaxies. We're looking at cosmic rays. We're looking at surveying the gas clouds in as much of the galaxy as we can using a radio telescope out at Coonabarabran. We're working on machine learning, trying to understand how we can pick out all of the galaxies in a gigantic amount of data that's coming our way in the next year or so. So there's a lot of different stuff that we're doing, and if people are interested, they can always
Get in touch.
They can always find us for a chat.
Yeah.
Great. Thank you so much, Nick. We really appreciate
Yeah.
the
Thanks a lot.
Thanks.
Fascinating discussion.
A lot of fun.
Yeah. Thank you.